Very good morning, dear friends. I'm sure your eyes must be tired seeing so many expressions, very dirty looking expressions. Generally, we have a practice of feedback from the student we call reaction survey in IIT Kanpur. And for many a times when I got the reactions from the student, there was one common observation: sir, your board work is very dirty. And immediately next semester I will try to improve it. But suddenly again the board work will become dirty. So few of my students again asked, sir, again I said I am statically stable as far as board work is concerned. Right? So that is where we are trying to see how I can fly a statically stable airplane. Why I am saying statically stable airplane? Because I know that airplane which is statically stable, it will not allow or oppose any change from the equilibrium. Right? We are trying to understand how can we fly a statically stable airplane. What is important to observe when I am talking about statically stable airplane? That statically stable airplane means it has an inherent initial tendency to oppose any change. That means if I am flying at 2 degrees, if I want to fly at 3 degrees angle of attack, CL corresponding to 3 degrees angle of attack, it will oppose. So I have to hold the control and take the airplane to 3-degree angle of attack and balance my forces and moments. Now about the equilibrium, it is again statically stable, so it will try to stay in 3 degrees. You want to change it to 4 degrees angle of attack, again it will oppose. So you have to put a control through the elevator, give a moment, come on, hold on, balance all the forces and moment. Again that becomes a new equilibrium. Again about the equilibrium, it is statically stable. Right? That is how we ensure that I can fly. Can design a control which should know very clearly that it is statically stable, and it has the inherent tendency to come back to the original equilibrium. That is the preamble of our discussion today. And to understand this in a manner through modeling, we wrote all those equations, lift on the wing, tail, and try to find out moment. And we got neat expressions. One was Cm naught as Cm naught wing plus Cm naught fuselage plus neta VH CL alpha tail into epsilon naught plus IW minus IT. And we got Cm alpha as CL alpha wing into XCG aircraft by C bar minus X AC wing by C bar plus Cm alpha fuselage minus neta VH CL alpha tail into 1 minus d epsilon by d alpha. And also we found our neutral point location as X AC wing by C bar minus Cm alpha fuselage by CL alpha wing plus neta VH CL alpha tail by CL alpha wing into 1 minus d epsilon by d alpha. This looks much neater, right? Whatever effort we made yesterday, the gist was these 3 expressions. Let us visit them as a designer. Okay? What is Cm naught? We know that if I want to fly at some CL or alpha, I need a particular value of Cm naught. We also have agreed if I have designed the airplane efficiently, I should automatically get the Cm naught without giving any elevator deflection. By giving elevator deflection, suppose this is the tail, by giving elevator deflection, I can generate moment Cm naught even at alpha equal to 0. So this graph can be shifted here, depending upon what deflection you have given. But for efficient design, I will ensure that I should be able to trim my aircraft as the CL or alpha without giving any elevator deflection. That means the Cm naught contribution should come from Cm naught because of wing then Cm naught because of fuselage, and then Cm naught because of tail. And we have not done any explicit expression for Cm naught fuselage, which is generally very low. And those who are interested, they can read books. They are very, very low. So we are more focused on Cm naught wing and Cm naught tail. And then second was Cm alpha. The message was what? That CL alpha wing, that is wing, that they should be placed, the AC of the wing should be placed in a manner, the tail should be placed in a manner that overall Cm alpha should be less than 0. The slope should be negative. Okay? Total contribution. And then we try to find out what is the limit at which I can lay out my CG, or I can take CG backward. At that point, the aircraft will become neutrally stable, or at that point, Cm alpha will become 0. The message is, if we take CG beyond that, then it will become statically unstable. Okay? These are the three interpretations. If you see in Cm naught wing, we have seen this is Cm AC wing plus CL naught into x bar, that is the difference between, I just said, let me write x by c bar. And we'll try to understand that one first from designer perspective. Okay? What a designer should do to ensure that Cm naught because of the wing is finally positive. May not be able to compensate for whatever Cm naught you require, but it will ensure that it is not negative. Okay? Because we are using cambered aerofoil. For a cambered aerofoil, CMAC wing is less than 0. So I have to do something with the second term. What is the second term? Second term is, if this is the AC of the wing, I will ensure that CG of the aircraft is behind AC of the wing. So at alpha equal to 0, I know there is a lift force or CL naught, and this distance is x. So this will give a nose up moment, or it will give Cm naught positive. And it should be sufficient enough to counter this negative value. At least this should become 0. Very good if you can get some positive value, because finally you have to get so much of Cm naught in combination with tail and fuselage. Okay? So the message is very simple. If it's a cambered aerofoil, try to put the AC of the wing ahead of CG. Although this will give a destabilizing contribution that you could see from here, the moment I put CG behind AC of the wing, this term is positive, this is positive, so whole wing contribution to Cm alpha is positive, which is destabilizing. But she said, don't worry, what is the problem? Our friend is here. So what is the problem? The stability part will be taken care by our friend tail, horizontal tail. So this is always negative. So I can go on changing the value of VH, which is tail volume ratio, and try to compensate for stability loss, static stability loss, because of wing AC being ahead of CG. Right? So message is clear. Don't worry about wing in terms of stability, static stability. Give some consideration so that it can help us in increasing Cm naught, because anyway cambered aerofoil, if you put the AC of the wing behind CG, the Cm naught from the wing will be further negative, so difficult in trimming. You put AC of the wing ahead of CG, it will have a destabilizing component. Doesn't matter, tail will take care. We will appropriately design the tail volume ratio, which is nothing but tail area into the tail momentum divided by wing area and mean aerodynamic chord of the wing. Right? Typically this value I have told you can start with 0.5, 0.6. Good enough. And this man tells you what? As you are designing the airplane, there is a configuration. You have selected some wing, some tail. This is the tail. the wing. And depending upon its location of AC, location of tail, because tail volume ratio contains LT, all these things you can get a fixed number for neutral point. So let's say neutral point is somewhere here. Okay. The message is, when you're layouting the CG, you will not move the CG beyond this line, beyond this point. And this gap between the CG and the neutral point, we call it stability margin. A stability margin, and it could be between 5 to 15% of the chord. This is a designer initial estimate. Okay. So once I understand this, now I ask a question. If I want to change the equilibrium of the airplane from one flight condition to another flight condition, how do I deflect my elevator? That is what we say elevator control, or we'll be talking about elevator control power. Our final aim to find out how much elevator should I deflect to trim my aircraft at a particular CL. Okay. So to understand that, let us do a little bit of reappreciation of the expressions, and we'll try to get an additional designer's perspective. You know, the Cm alpha wing is xCG by C bar minus xAC wing by C bar plus Cm alpha fuselage minus neta VH CL alpha tail into 1 minus d epsilon by d alpha. Okay. I divide left hand side and right hand side by CL alpha wing. So what we'll have? I have Cm alpha of the whole aircraft by CL alpha wing. This is equal to xCG by C bar minus x AC wing by C bar plus Cm alpha fuselage by CL alpha wing minus neta VH CL alpha tail to 1 minus d epsilon by d alpha divided by CL alpha wing. Okay. Now what was the expression for neutral point? See, x and p by c. If you see, it was x AC wing by c minus Cm alpha fuselage by CL alpha wing plus neta VH CL alpha tail by CL alpha wing into 1 minus d epsilon by d alpha. These are the expressions already you have. Now carefully see the right hand side. If I just manipulate this, I can write this equal to xCG minus x and p. You could see if I take minus sign common here, then xAC by wing minus Cm alpha fuselage by CL alpha wing plus neta VA CL alpha tail by CL alpha wing 1 minus d epsilon by d alpha, and that is nothing but x and p by c, location of neutral point. So this ratio is nothing but xCG minus x and p. That is, if this is the aircraft, if I am measuring the xCG, this is xCG, and this is the neutral point, x and p, then this difference, as I told, is static margin. So this is equal to minus of static margin, because static margin is defined as x and p minus xCG. Okay? So minus of static margin. So what we have got in a simpler term, we got Cm alpha of the aircraft by CL alpha wing is minus static margin. Now if I do an approximation, this is what a designer plays an important role, right? Because we are trying to get the initial estimates. You know, what is the primary role of the wing? Generate lift. So it's obvious the CL alpha of the wing, based on the reference area, is the predominant CL alpha of the whole airplane. That is, I can assume with a 10 to 10% inaccuracy that CL alpha of the aircraft is nothing but CL alpha of the wing. That is, CL alpha of the aircraft is approximately equal to CL alpha of the wing. This is an approximation. This is I am doing because I understand that CL alpha of the tail based on the wing reference area will be very small compared to CL alpha of the wing. So this is what the whole trick to get a designer's feel. Then I can write Cm alpha of the aircraft by CL alpha of the aircraft. And I write Cm alpha of the aircraft divided by CL alpha of the aircraft. And this is nothing but dCm by dCl of the aircraft. Hence, I can write with this approximation dCm by dCl of the aircraft is approximately equal to minus static margin. This is a wonderful result for a designer to design an airplane. That is why I am stressing at this point. Okay? You see how beautifully we use this for designing an airplane. So the problem what we are looking for is, suppose this is your Cm versus Cl graph, and the slope is dCm by dCl, and that is, we have agreed that dCm by dCl approximately is minus static margin, and if it is 15%, so I write minus 0.15 C bar, okay, or minus 0.15, that is 15% static margin, which is, as far distance is concerned, 15% of chord, mean aerodynamic chord. This is the separation between neutral point and the CG. CG is ahead of neutral point, and it is statically stable. Okay? Right, this is minus 0.15. Now what we are trying to do is, I want to know if I am flying at this CL, or if I am to fly at this CL, another CL, I know by virtue of it being statically stable, it will generate a negative moment, nose down moment. So I have to counter that and make sure that the Cm versus CL graph passes like this from this equilibrium. The question is, how much moment, positive moment I should give to compensate this negative moment? That will be given by Cm versus CL graph. How do I generate this? I generate this positive moment now to counter this negative moment by giving what the elevator up, deflection. So that elevator up, or the elevator up deflection should generate enough moment, pitching moment, positive, to counter this negative moment, so that at this point, again the moments are zero, so they are at trim, or they are at equilibrium. Okay? So if this understanding is there, then we will formulate. Let us see, so far we are talking about CL as function of alpha for a given Ehlers number, Mach number, etc. So we wrote CL as CL naught plus CL alpha into alpha, right? Now if CL is also, you could see, not only function of alpha, it is also function of delta E. Do you agree with me or not? Suppose this is the wing, this is the tail, right? And total CL, suppose this is alpha, then CL is CL naught plus CL alpha into alpha for the whole aircraft. CL alpha is for the whole aircraft. But if I now give a deflection of the elevator like this, which is positive deflection, then even at alpha equal to 0, this will produce a lift. So now my CL will also become function of delta E, right? So in a partial derivative sense, since we are assuming everything to be linear, I say the CL I can write as CL naught when both alpha delta E were 0, then find out what is CL alpha. That is, CL alpha is the per unit change in CL because of alpha, holding elevator and other things constant. Then I say, okay, add CL delta E into delta E. CL delta E means how much change in CL because of unit deflection of delta E, holding other things constant, no change in alpha. So this will give me a description of CL. And Please understand all these values CL naught, CL alpha, CL delta, they can be estimated depending upon geometry and flight conditions. So you assume that these are available for a given geometry and given flight condition. So if this is true, the moment I am deflecting it by delta, it not only giving some CL or delta CL, it also gives a moment, right? So now I must modify the moment equation also. So far how I was writing moment I was writing moment coefficient, I was writing as Cm naught plus Cm alpha into alpha. Now what has happened? Because of delta E deflection of elevator, there is a increase in CL, or there is a change in CL. Change is the correct word. It may increase, it may decrease the overall CL of the airplane depending upon which way it is deflected. Not only it will change the CL, but this force will create moment about center of gravity, so it will also give pitching moment. Depending upon it is elevator is up, then it will give a pitch up moment. Elevator is down, it will give pitch down moment. Okay? In this case, it will give pitch down moment or nose down moment. If it was up like this, it will give pitch up or nose up moment. So I need to add Cm delta E into delta E, where Cm delta E, I say the additional change in the pitching moment coefficient because of delta E, or in terms of dimensional quantities, I say additional pitching moment generated because of elevator deflection, all about center of gravity. Thank you.